Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. So for the assignment of Opto-Electronic, we are given the task to present on the topic of Fabry Perot Homojunction laser diode. So first we are from group 1. So let's go to the table of content. There will be 7 subtopics that we will cover today. Which is on the first one is introductions, and then advantage and disadvantage. Next is on the homojunction. Also we'll cover on what is Fabry Perot. Next we will cover on how the laser works, and then on the applications of laser, and on the last one is on the conclusions of this topic. So for the introductions, how to understand the operations of the Fabry Perot laser. To understand the operation of Fabry Perot laser, it is first necessary to understand the Fabry Perot filter. So Fabry Perot filter, the principle of the Fabry Perot filter is illustrated in figure 1, which is on the below of this slide. It said when you put two mirrors opposite one another, they will form a resonant cavity, and then light will bounce between the two mirrors, and when the distance between the mirrors is an integral multiple of half wavelengths, the light will reinforce itself. Wavelengths that are not resonant undergo destructive interference with themselves and are reflected away. Next, still on the introduction, we will consider a laser to be Fabry Perot when it has a relatively short cavity, which is in relation to the wavelengths of the light produced. Wavelengths produced are related to the distance between the mirrors by the following formula. CL, which is length of cavity, is equal to wavelength times to an arbitrary integer with the 1, 2, 3, 4, and we will divide with 2 times with refractive index of active medium. Notice here that the only other variable in the equation is the refractive index of the gain medium, which is directly in the cavity. This is because we always quote the wavelength as what it would be if the wave was traveling in a vacuum. And since the speed of propagation in the cavity is a lot lower than c, which is the speed of light, the wavelength is a lot shorter than it would be in free space. The adjustment factor is the refractive index. So now I will pass to Nuruddin for advantage and disadvantage.
Let's take a look for the advantages of the laser. There are 4 advantages of the laser that we got. The first one is compact and inexpensive laser diodes, and the second one is extreme narrow spectral width, line width, and the third one is laser can be modulated very fast, and the last one is source of the coherent light. Okay, so next we move to the disadvantages of the laser. The first one is laser need temperature and output power control, which is high cost, and the second one is for the optical communication system, a cooler Peltier effect is needed, and the last one is analog modulation is difficult due to non-linearity of the output power, which is, for example, is currently sold. So next, we must know what is homojunction. So a homojunction is a semiconductor interface that occurs between layers of similar semiconductor material. So there is the picture of the homojunction, which have a layer. So at the picture we can see the surface, mirror, electrode and active region. The homojunction occurs at the interface between N and P type, we called as PN junction.
What is Fabry Perot? Fabry Perot is a laser oscillator in which two mirrors are separated by an amplifying medium with an inverted population, making a Fabry Perot cavity. Fabry cavity is a standard cavity with two highly reflecting mirrors bouncing the light back and forth, forming the standing wave. And then Fabry Perot is by definition consists of two planar mirrors, but the term is nowadays very frequently also used for resonators with curved mirrors. And then this figure, this is the figure which illustrates the Fabry Perot cavity. You can see where the light in when enter on the first mirror, it will reflect, and some will just throughout the second mirrors, while some part will reflect back and go through the second mirrors. Then light will be out, and then the maximum light transmission can be calculated when n, which is integer, is times to the wavelength of light, which is equal to 2 omega cos alpha. So now I will pass to Haikal for the next part.
There are 5 laws that we have to know for Fabry Perot laser to work. For the first picture, it has an active region at the center and two parallel mirrors at the end. This is also called a Fabry Perot resonator. The two mirrors and the active medium between them form a laser. This is shown again in the first figure. We need a mirror to provide a positive feedback, that is, the return of the stimulated photon to an active medium to stimulate more photon. The two mirrors themselves form a resonator with length L. For the second picture, let a random wave travel from the left hand mirror to the right hand mirror, as the second picture shows. At the right hand mirror, this wave is reflected, hence the wave experiences a 180-degree phase shift. As you can see, the wave should have a break in its wave, which is impossible here. In other words, this resonator does not support this wave. Now let another wave, as shown in the third figure, travel inside a resonator. At the right hand mirror, the wave experiences at a 180-degree phase shift and continues to propagate. At the left hand mirror, this wave again has the same phase shift and continues to travel. Thus the second wave yields a stable pattern called a standing wave. The only difference between the two waves is their wavelength. Thus a resonator can support only a wave with a certain wavelength. The wave that form a standing wave pattern, this resonator support many wavelengths that can form a standing wave. Wavelengths selected by a resonator are called longitudinal mode. Now how many longitudinal mode can a laser diode radiate? A resonator can support an infinite number of waves as long as they form a standing wave. However, the active medium provides gain within only a small range of wavelength. Since laser radiation is the result of the interaction of a resonator and an active medium, only a several resonant wavelength that fall within gain curve might be radiated. The light degeneration starts only when gain exceeds loss. Thus, eventually, only those resonant wavelengths that are within the gain over loss curve will actually be radiated. Compare these two figures, only these three waves will be the actual laser output. The other two modes are not generated since their loss is bigger than their gain. Now let's move to output spectra of FP laser. Fabry Perot laser provide long feedback, which result in many long longitudinal mode and eventually in a relatively large spectral wave. This picture shows the output spectrum of a 1.55 micrometer FP laser. FP lasers are capable of FP lasers are capable of producing high power but are typically multimode at higher operating current. For the next part, we move to the application of the Fabry Perot Homojunction laser diode.
Okay, we move to application of the laser. For the assignment, we come up with two application of the laser, which is the first one is laser rangefinder. What is the laser rangefinder? A rangefinder that use a laser beam to determine the distance of object, which is used for military and 3D modeling. Okay, the second one is Fabry Perot interferometry. So what is the Fabry Perot interferometry? Extrinsic FPI, as now EFPI, is the underlying principle of the many recent generation of pressure sensor that based on the optical fiber. Okay, after this I will explain more about these two application of the laser. Alright, I will explain more about Fabry Perot interferometry. So what it is? So I give a picture for this for understand clearly this. Okay, the structure of pressure sensor is known as A. Okay, A is a structure of EFPI pressure sensor, and B and C is manufacturing procedure. So there are procedure of manufacture, which is 1, 2, 3. Okay, in B and C we clear the procedure of manufacturing. So EFPI have some operating concept. So what the concept? Okay, the first one is fabricating a Fabry Perot cavity and semiconductor laser on the tip of the optical fiber, a well-known principle in electromagnetic filter and resonator. So the second one is enclosing FP cavity with a flexible diaphragm which bend and compress the FP cavity when the pressure is applied to diaphragm surface. Okay, verify its length. A glass capillary form a quad frequently surround the whole structure, sealing it and encase the FP cavity. Okay, so we move to the second application, which is laser rangefinder. So there is example of laser rangefinder. Actually, this is a device that work by emitting laser beam at the and there is a button to turn off and turn on it. So this actually device is used for measure the distance. So the first one is used for military. So it provide an expected distance to target to sniper, which is this actually used for sniper to measure the distance of the target. Measure the distance is up to 20 km. Installed on tripod, vehicle and gun platform. Okay, the second one is used for the 3D modeling. So in 3D modeling, used in 3D object recognition, 3D object modeling, and verify of computer version relate field. So as we know, used in computer version application often have deep resolution of 10 of millimeter or less by using triangulation or refraction measurement technique. So actually both of these used for measuring distance. So by using this device we can get accurate distance.
In conclusion, the significant disadvantage with the Fabry Perot execution diode is that the current threshold density which is JTH far too high for practical use. JTH grows at a temperature too high, not continuously, but impulse laser output. And then laser wave homojunctions has poor optics and reduced containment of the carrier. If JTH low, this will increase emission stimulation rate and improve optical cavity efficiency. In order to get a low JTH, confine carriers in a narrow region to carrier confinement and build dielectric waveguide around the optical gain region, which is increased photon concentration as stimulated emission to photon confinement. And how do we achieve that? It is by heterostructured laser diodes. So as the conclusion finished, so that's our presentation. Thank you very much.